Hey everyone, welcome to part 2 of the trees problems walkthrough, and we're starting off with count good nodes in a binary tree. So in this question, given a binary tree root, a node x in the tree is named good in the path if in the path from root to x there's no nodes with a value greater than x. So in example 1 here, 3 is good because there's no values from the root to the root with a value greater than 3. 4 is good, 1 is good. 5 is good. However, 1 is not good because 3 and 4 on this path from the root to itself, 3 and 4 are both greater than 1. This one here is also bad because 3 is also greater than it. So in example 2 here, all the blue ones are good except for 2 because the 3's are greater than 2, and the 3's are on the path from the root to the 2. So how should we approach this question? Well, all we have to store is the greatest value of any node on the path from the root to the node when we traverse at the node. So to solve this question, we can use a BFS approach. A DFS approach works too, but BFS is easier to implement. So let's start off by creating our answer. Answer is the number of good nodes we have in the tree. So BFS, just like the previous question, let's start off with creating a DQ. And in the DQ, we need the root, but not only the root, but also the greatest value coming from the root. So at the root, it's just root.val. So we just have the DQ, and then the DQ has a tuple with the root and the root's value. So while len BFS is greater than 0, so while there's still nodes to BFS, we're going to just pop out the node and the max parent value. So max parent value, in the first case, is just going to be root.val, but later on, it's going to be the maximum value of any of its parents coming from the root. So this is going to equal bfs.pop left. So notice we don't need to pop out this BFS row by row, like level by level, because we don't care about any attributes of the levels. All we care about is traversing all of the nodes in level order so that the nodes have the greatest parent value stored. So how do we see if a node is a good node? Well, we have to compare its value, so node.val, to its parent's value. So if its value is greater than or equal to the parent's value, so max parent val, we can say it's good. So answer plus equals to 1. So now we have to calculate the new max parent val. So new max val. This is going to be the maximum of the node's value and the previous parent's value. So max parent value. So now we should also put the children into the BFS if and only if they're not none. So if node.left is not equal to none, BFS.append. What are we appending? We're appending a tuple with the node first, so node.left, and also the maximum parent value, so max parent val. Actually, it should be new max val that we just calculated because it includes the node's value. So if node.right is not equal to none, bfs.append, node.right, and new max val. So after that, this while loop traverses the entire tree with BFS, so we can just try to return the answer after that, and let's try returning answer. Nice, let's try submitting it. Cool, okay, that worked. So moving on to the next question, validate binary search tree. So validate binary search tree. Remember, a binary search tree is defined as the left tree containing nodes with keys less than the node's key, and the right subtree as containing nodes that are greater than the node's key. So both the left and right subtrees must also be binary search trees. So in this example here, 2 is the root. Any child on the left of 2 has to be smaller than 2, and every child on the right of 2 has to be strictly greater than 2. So in the first case, this is true because 1 is strictly smaller than 2, 3 is strictly greater than 2. In example 2 here, the answer is false because we have a root of 5, but 5's right child, 4, is less than 5. So this is not a valid binary search tree, so we return false. So to code this question, the question basically says it for us. We need to check that the current root, the current node, is strictly smaller than the left, strictly greater than the left, strictly smaller than the right, and also the children have to be binary search trees as well. So we need boundaries for the current node and its children nodes. So let's create a recursive function, def validate. So it passes a node and the minimum value and the maximum value. So because we need the current node to be bounded by the minimum and maximum values. So if we call this on the root node, we're going to return validate root. And also, so for the root node, the minimum value it can take is float negative infinity. And the maximum value it could take is float positive infinity. So this is basically no boundaries, but we're going to set the boundaries as we traverse down the node. So let's do a none check first. If node equals to none, return true. And if node.value, so now we're comparing with the minimum value and the maximum value. So if node.val is less than or equal to minimum value, or node.val is greater than or equal to the maximum value, we're returning false because it's not a valid binary search tree. So now looking at the left child, so left valid. The left child, we need to validate that the 1 and all of its children is smaller than 2 and greater than negative infinity. So how we do this is we use this recursive function recursively, so validate node.left. Its children at itself have to be all greater than the minimum value, which is still negative infinity, but they also have to be less than the node's value, so node.val, which is 2 in this case. So 1 and all of its children, if it has any children, have to be greater than negative infinity and smaller than 2. So also right valid, doing basically the same thing, validate node.right, except we need to set a lower bound. The lower bound is going to be root.value, or actually it should be node.val and max.val. Because for 3 and all of its children, they have to be smaller than positive infinity and greater than 2, because 2 is the node's value here. So we're going to return left valid and right valid because we need both of them to be valid. And let's try running it. Cool, let's submit that. Nice. So this question, we basically, at every node, we need to check that it's within a specific range, which is bounded initially by negative and positive infinity, but as we move down the tree, it's going to be bounded by its parents' values. So we can recursively check that every node is bounded by these values, and if it is, then we return true, otherwise we return false. So moving on to the next question, kth smallest element in a binary search tree. So given the root of a binary search tree and integer k, we want to return the kth smallest value, 1 indexed, of all the values of the nodes in the tree. So in example 1 here, we can see the tree is 3, 1, 4, 2. We want the k equals 1, so the first smallest value, so that's going to be 1 because that's the 1th smallest value. In example 2 here, k is 3, so we want the third smallest value. So the values go 1, 2, 3. 3 is the third smallest value, so we return 3. So how do we know the position or how many values there are for a node? We need to see how many there are on the left of it. So 3 is the third smallest value because there are 2 nodes on the left of 3. So 5 is going to be the 5th smallest value because there's 4 nodes, 1, 2, 3, 4 on the left of 5. So 5 is going to be the 5th smallest value, and so on. So we need a helper function, count, to count how many nodes there are on the left of a certain node. So let's create this count, def count, node, and if node equals to none, there's nothing, so return 0. Otherwise, we want to return 1 plus count node.left plus count node.right. So count counts how many nodes there are within a subtree. So for example, if we do count at the third node here, 3, it's going to return 4 because there's 1, 2, 3, 4 nodes in the subtree. So we can take advantage of this helper function count and calculate the position that the root is currently in. So position equals to 1 plus count root.left, because the position is the number of nodes on the left of it. So for example, 5 is in the 5th position because there's 4 nodes on the right of it and we do plus 1. So it's in the 5th position. So if position equals to k, that means we found the node in the kth position, or the kth smallest node. So all we want to return is node.val. Should be root.val. However, if position, let's do elif, position is greater than k, so the position is too big, so we want a smaller position. So how do we find the nodes that are in smaller positions? Well, it's going to be on the left because it's a binary search tree. So return self.kth smallest root.left and k. So otherwise, the position is too small. So if the position is too small, we're going to have to look on the right side of it. So return self.kth smallest root.right. However, we're not caring about the kth position anymore. We're caring about k minus position. The k minus position. Because we already know that on the left of the 6, for example, there's going to be 5 or position elements. So the element 6 is at the first position because k minus position, k minus 5 is 1. So all we care about is the position after removing the number of nodes on the left of it. So let's try running that. Cool, let's submit it. So this question takes advantage of a helper function called count. Count basically counts how many nodes there are in a subtree, so we can determine the position every node is at. So, and then we will make a decision based on what position is. So if it is equal to k, then we're going to return. If its position is greater than k, we're going to look on the left side. Otherwise, we're going to look on the right side. So moving on to the next question. So construct binary tree from preorder and inorder traversal. So we're given 2 arrays, preorder and inorder, representing the preorder traversal and inorder traversals of the same binary tree. We want to construct and return that binary tree. So in example 1 here, the preorder goes 3, 9, 20, 15, 7. That's because preorder takes the value of the node first, then its left child, and then its right child. So it'll be 3, 19, 20, then the left child of 20 is 15, the right child of 20 is 7. So inorder is basically the order of the binary search tree if it were a binary search tree. So 9, 3, 15, 27. So we're given these 2 arrays, preorder and inorder, and we want to construct the original tree from these. So one thing we can notice immediately is that in preorder, the first element is going to be the root. So we can take advantage of that because this splits the children into the left side and the right side. So looking at the inorder, the root 3 is at the 0, 1, the 1th index. So everything on the left of 3, because it's in order, is going to be on the left child of 3, and everything on the right of 3 is going to be on the right child of 3. So we can take advantage of that fact by knowing that the root is always going to be the first element in preorder, then splitting inorder into 2 different arrays, the left side and the right side, and then we can call build tree recursively to build the left child and the right child of the root. So let's try constructing it. First, we should do a null check. So if len preorder equals to 0, that means we're not given any elements and we should return none. So basically an empty tree node. So now we should create the root. Remember, the root is always the first element of preorder. So we can call it tree node preorder at index 0. So we have the root now. Now we want to find how many elements there are on the left and the right children. So we need to find this 3 here and how many elements there are on the left and the right of it. So let's traverse in order the array in order and find the index of 3. So index equals to 0 for I val in enumerate. Or what are we enumerating? We're in enumerate in order. So if val equals to root.val, so if it equals to the 3 here, we want to set index to I and break out of this loop. So now we've found the index of the 3 or the root. So everything on the left is going to be the left child, everything on the right is going to be the right child, because the inorder array is in order. So left in order and right in order. We can partition this in order array into the left and the right sections. The left being in order from 0 all the way to index. This doesn't include index in Python syntax, and we want the right side. So in order from index plus 1 all the way to the end. So remember that the preorder array and inorder array always have the same size. So we know that the left preorder array has to have the same size as the left inorder array. So we can get left size equals to len left in order. So now we can create the left and the right preorder arrays. So left preorder, right preorder. This equals to preorder partitioned from 1. Remember, we want to start from 1 because the first element is the root and we've already used that value. So we don't want to use it again all the way until left len plus 1. And the right side is going to be preorder from, not left len, left size, from left size plus 1 all the way until the end. So we have the left and the right preorders now. We can create the left and the right children recursively. So we're going to call this build tree recursively with root.left equals to self.build tree, left preorder, and left in order. So we can do the same thing for the right, root.right equals to self.build tree, right preorder, and right in order. So after those are done, we can just return the root because we built all the children recursively, and we just return it. Let's try running that. Submit it. Cool, okay, that worked. So in this question, we're taking advantage of the fact that we know the first element of preorder is always going to be the root wherever we are. So we can partition in order into the left and the right subarrays. And then using the length of those subarrays, we can find out how many elements we want to take from preorder into those left and right subarrays, and use those partitioned left and right preorders and inorders to create the left and right children. So let's move on to the next question. Binary tree maximum path sum. So a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. So a node can only appear once in the sequence, at most once in the sequence. Note that the path does not need to pass through the root. So a path sum is the sum of the node's values inside that path, and given the root, we want to find the maximum path sum. So in example 1 here, the maximum path sum is easy because everything is positive. We just add everything up. We get 1 plus 2 plus 3, that's 6. So in example 2 here, there's negative numbers, so we probably don't want to use those negative numbers unless we can use those negative numbers to get better numbers. So in this case, the output is 42 and the optimal path is 15, 27. So in this case, we don't want to include the 10 at the 9 because that gets us a net of -1, and that's less than optimal. So this question is actually very similar to a question we've done previously for maximum diameter of a binary tree. So we always need to return 2 things with our recursive function in that question. We need to return the maximum height from a certain node and also the maximum diameter of starting from that certain node if it passes through that node. So in this case, it's quite similar. We want to return 2 things. We want to return the maximum path sum starting from a certain node. So for example, starting from the 2 all the way to its children. In this case, there are no children. And also, we want to get the maximum path sum of the values passing through this. So let's create our function here, def max sum, and it takes a node. So we need both of those things to actually calculate the maximum sum. So if node equals to none, let's do a null check first, return 0, float -infinity. because if it's null, we want to use negative infinity so we don't accidentally return a negative value when doing the comparison. So left, let's let left from and left across be the maximum path from the left all the way to its children, and the left across be the maximum path sum across left's child. So this equals to max sum node dot left and left. So we can do the same thing for the right side here. Right from, right across equals to max sum node dot right. So max from, now we have the maximum starting from the left child, the maximum starting from the right child. So if we were to have the maximum path across our current node, then the maximum across here would be node.val, because we need to include the node, as well as left from and right from. But we also don't have to include these in case they're negative. For example, if this is -2 here, we don't want to include left from. So an easy way to do that is just calling left from and comparing that with 0. So we're going to return the maximum of that in 0. Same thing for right. Oops. Max right from 0. So we have the max across of our current node now. Now we also need to get the max from. So max from can only go down one of the two ways instead of going across. So max from equals to node.val plus maximum of 0, left from, and right from. We're comparing these with 0 just in case left from and right from are both negative, in which case we don't want to take any of them. So for our answer, we're going to return max from first. That's what we defined our function to be returning, and also the maximum path sum from the current node. So the maximum path sum, it could be max across, or it could be left across, the maximum of the left child, or it could be right across, the maximum of the right child. So we're not sure either if it's any of them, so we need to return the maximum. So now after that, we can just return max sum, calling it on root, because we're starting with the root, and also taking it index 1. Because remember, the first index 0 is max from, but we actually want to the maximum path sum. So that's going to be at index 1. Let's try submitting that. Cool, accepted. I'm gonna submit. Nice, that worked. So this question is actually pretty difficult, but it's very similar to the maximum diameter of a binary tree, because we need to, in that question, we also needed to return two things: the maximum height starting from this node and the maximum diameter across this node. So this question is very similar. We're returning the maximum value from this node, for example, left from and right from, and also the maximum diameter or the maximum path sum that goes across this current node, as in max across. So then we compare to see which one is actually the greatest and return that in the end. So this is quite a difficult problem, but we've seen a similar one before. So moving on to the next question. Serialize and deserialize a binary tree. So serialization is the process of converting a data structure or object into a sequence of bits stored into a file or memory buffer, transmitted across a network to be reconstructed later. So basically what this question is asking us to do is to take a binary tree starting at the root, and then we're going to serialize it into a string. So basically store that binary tree as a string, and then later taking our string, reconstructing that binary tree, and getting the tree back. So let's take a look at the example, where the example doesn't show much because it just gives us the tree, and then the output after serializing and then deserializing should be that same tree again. So the trick to this question is to find a way to store this tree as a string. So there's multiple ways to do this. We could do it with BFS or TFS, and then the way that's pretty simple and easy to understand is probably going to be preorder traversal. So in preorder traversal, we're going to store the value of our current node into the string, And then we're going to store the value of the left and the right children. So if there's any null children, for example, 2 has a null left child, it has a null right child. So we're going to store a special character, something like an underscore. So let's try coding this up. So let's create our answer. Answer is the serialized binary tree in an array form. So def preorder, calling it on a node. So if node equals to none, we want to put a special character. So let's put underscore here, and also return, because we don't want to call preorder on a null node. So after that, we can append ans and the node's value. We need to cast it to a string, because in the end, we're going to have everything be a string. And then we can call preorder on the left and the right children. So we don't have to check if the left and the right child are null, because we're doing the check inside preorder. Before we didn't do that check, so we had to check before inserting it. So with this preorder function, we could just call it on root. So preorder root, and then we can just return. We need to return this as a string, so let's separate them by commas and join ants. So this basically concatenates the answer array into a single string separated by commas. So that's our preorder traversal, and now we have to take that preorder traversal in string form and then put it back into a tree. So we need to first split up this data and then put it into a queue for preorder traversal. So values equals dq data.split. We're splitting by the comma because we separated everything by commas earlier. So we can define another preorder function that takes in, it doesn't have to take in anything. So the value first is going to be values.pop left. We're taking the first value because preorder always stores the root node's value first. So we're going to take the leftmost, that's going to be the root's value. And if value equals to underscore, so this is the special case where it equals to none, we're not going to return anything, so we return none. This is basically a null tree node. So if value is not an underscore, that means it actually has a value. So we can create a tree node with that. So let's cast it to an int, because we're casting from a string into an int and then creating a node with that. So node.left equals to preorder. We can just do the same thing as encoding it, except we're using this dequeue here. So preorder, we're going to store the node's value, then its left children, then its right children. So using a queue here makes sense because we're taking the value out, then we're taking all the left children's values out with node.left, and doing the same thing for the right children. So preorder. Node.right equals to preorder. After we created the left child and the right child, we can just return the node. So return node. So we can now just call preorder. Calling preorder on the full value set will create the root and all of its children. So we can just return preorder. Let's try running it. Values is not found. Oh, okay. Missed an S there. Nice. So this question takes advantage of the preorder traversal strategy in binary trees. So basically we're preorder traversaling the tree, storing all of its values and null values as a special character, and then storing that in a preorder array, and then casting that array to a string separated by commas. So to deserialize that, we separate the string by commas back to the array, so we get the values. We use a dequeue, so we always get the first value first, and the first value is going to be the value of the root. So after that, it's going to be the values of the left child of the root and the values of the right child of the root. So we do node.left, node.right, all calling preorder to get values from the value dequeue, and in the end, we're returning a root. So calling preorder on the whole value set, we're going to create the root, all of its children, and we can just return that. So that was this question, and that's the end for the trees question from the LeetCode roadmap. Thank you guys for watching. Hope you guys were able to learn something, and I'll see you in the next video.